Hello, my name is Yvonne from Team 252A, and today I would like to introduce a new way of making your autonomous programs more consistent. I'm pretty sure that most teams will rely on the inertial sensor to write their PID code. We did the same thing as well, however, we found out that using the inertial sensor alone wasn't a very good idea, as there were a couple of problems. For one thing, when the robot is driving off course and the PID corrects itself, it will return to a heading of 0. However, there is no guarantee that the robot is still driving on the same line as it was before. Due to this, we did a lot of experimenting and we found out that combining the inertial sensor with the distance sensor would solve this issue and make our autonomous programs more consistent all around. Alright, so now let's talk about the math behind the distance sensor. There is a robot that is driving in this direction and heading, with two purple lines representing the distance sensor values. Line AE represents the distance sensor's values if the robot is driving in this slanted position. However, this is not accurate because obviously the robot is not driving straight. So what we really want is this line, line AD. Line AD should represent the distance value if the robot was driving perfectly straight, henceforth why it's perpendicular to this line that represents heading 0. We can also look at the angles. Let's call angle BAC over here as angle theta and angle CAD as angle alpha. We know that theta plus alpha equals 90 degrees, and because alpha plus angle DAE also equals 90 degrees, we know that DAE must equal theta as well. So given this, we can derive the fact that AD over AE equals cosine theta, and given this, we can quickly derive that AD equals D times cosine theta. So to summarize, given a distance sensor's value and the current brain inertial rotation in degrees, you can solve for AD. Alright, so now let's talk about the code. Before I start, I want to talk about the concept of the distance sensor. So it's actually very similar to the old concept that we use for the regular PID using the inertial sensor. The only difference is that we are now doing distance correction and not heading correction. To put it in other words, the error will be the difference between the two distance values instead of the heading values. So let's look at the code. So here in this OR condition, what we're trying to do is we're going to compare the drivetrain motors to our desired target. So we can add the two positions together. We divide this by 2 to find the average. And then we can compare this to the target using an operation sign, like that. And then we just snap it in. Okay, so now let's talk about the motors. So, as mentioned before, it should follow around the same structure as the previous one, where we multiply the KP with our error, and contained inside the error will be the math that we talked about in the previous section. So we can multiply the distance sensor's values with the cosine of the brain inertial rotation in degrees, multiplied by the cosine of the brain inertial rotation in degrees. We will subtract the distance from this, and then we multiply our KP value. Note that this KP is different from this KP as we are not talking about the same thing anymore. So multiply this by KP, and then in the end, we'll multiply this by the velocity. And then we can just directly use it. That, and it should be the same for the right motor as well. Alright, so there's actually two thinking questions that I want you guys to think about.